Okay, so let me see something about the next homework assignment. Okay, so let me say a couple words about the homework. If you love computer science, you might have heard number one. You say a Boolean ring is a ring such that when you square anything in the ring, it's itself. Like square you collect for all its R. Show that a Boolean ring is commutative automatically. Right? This is sort of reminiscent of that problem that every group of exponent 2 is dealing, right? A Boolean ring is always commutative and has characteristic 2. And we're going to talk about what the characteristic means, but that means if you add anything to itself, you get 0. Number 2, show that if R is a commutative ring, then the set of nilpotent elements is an ideal. And give me a counterexample in the non-commutative case. Number 3 is kind of I think it's, well, at least I found it kind of useful to do it in this order. 3 is kind of a fun problem. Suppose you have a non-zero ring that has the property that for all non-zero A and R, there is a unique, that'll come up. There's a unique B and R such that ABA is A. All right. So one might almost consider B as an approximation to the inverse of A. Right? But this is more general than that. Show that R has no non-trivial zero divisors. With the notation above, show that BAB is also equal to B, so ABA is A. Show that BAB is also B. Show that R has an identity. And finally, show R's division. So you can lose some division into that characterization or that condition right there. Number 4, show R is a commutative ring of prime characteristic. So that means that when you add anything to itself B times, you get 0. Show that the function Bn from R to R given by Bn x is x to the p to the n is a ring homomorphism. This is often, how many of you have heard of freshman string? This is a generalization of this where in characteristic P, x plus y to the p power x to the p plus y to the p. And if you've ever graded a Calc 1 class, you know why it's called freshman string. Number 5, an element E and R is said to be an idempotent if E squared equals E, well, like in number 1. And E is said to be a central idempotent if E is idempotent and it's in the center of R. So that means that it commutes with everything multiplicatively. Show that if R has an identity and E is a central idempotent, then 1 minus E is also a central idempotent. And B, show if R has an identity. If R has an identity, show that ER and 1 minus ER are ideals for R, and R is isomorphic to the direct product. Okay, hopefully that will be kind of a fun beginning homework set for talking about rings. Any questions? So let's get back where we were. Okay, so let me give you kind of the next theorem. The last thing we talked about was that interesting theorem that we had with corollary was any finite interval domain field. So let R be a ring with identity. Let's say n a natural number and ABAI is R. And these symbols will denote elements of R. If AB equals BA, that is if A and B commute, then This is called binomial theorem, as you may have seen before. And two, if Aij for all I, this is the more general multinomial form of actually AS. So here's the more general thing. So it's powers of this, K1 of S. And what's my multiplier? Well, it's more general. And this sum is taken over so notice that this one sort of subsumes this one, right? Because this is the case where S equals 2, and you're taking all the sums where they add up to n, so hence the exponents here, and this collapses to the binomial coefficient. See if you can prove this by induction. It's not terribly hard, but it's a good induction exercise. This is called multinomial. Definition. So now, as I promised before, there's a lot of kind of recurring themes, right, in algebra. And one of the central notions when we did group theory was the notion of a homomorphism. Let's extend this to rings. The function B S is said to be a ring homomorphism. Okay, well, this first one, all this first condition says is, hey, what is a ring first and foremost? First and foremost, a ring is an abelian group. And this is respecting the group, baby. What this is this just means that actively this phi is a homomorphism of the abelian group structure. But rings are not just abelian groups, they've got this extra structure because they've got this extra multiplication. And my homomorphism is going to respect that. So I think this is what you would expect it to be. It's just a homomorphism that hits on all cylinders. It respects the addition, so it's an abelian group homomorphism, and it respects the multiplicative operation. Let me point out, before we move on to a couple of examples, that my usual adjectives apply, right? So if I say a ring monomorphism, one-to-one ring homomorphism, an epimorphism, et cetera, et cetera. So let's plot some homomorphisms. So here's some examples. Here's one of my favorites. Notice the integers is a ring, and Z mod n is a ring with addition and multiplication given mod n. This homomorphism is just, it takes whatever k is, and by the symbol here, I mean the equivalence cost of k or the reduction of k mod n. We already know this is homomorphism of groups. CT checks the homomorphism of rings. It's a pretty standard thing. And in fact, this is actually a special case of a larger type of homomorphism we'll talk about later. Here's an example for homomorphism. Projection in the first factor. You could also do a projection in the second factor. There's also a iota from R and R, iota of R. That's a ring homomorphism as defined so far. Let me make a net. Let me do one more here. Here's a good example. Here my ring is polynomials with coefficients in Z and two variables, right? This might be something that you see in Calc 3, right? You do a lot of polynomials there, except my coefficients are only in the integers. I want to go here. Here, give me two integers. Right off the trigger of that one, weren't you? So, in honor of his choices, I'm going to call this piece 3,7. Right. Notice that my input is a polynomial in two variables. My output is an integer. It's got an integer coefficient. I'm going to plug that in. Notice that this is sometimes called an evaluation of homomorphism. Let me make a note here. So, and this is like if you ever read an algebra, assume if B of R and S are rings, then assume B R. And I'm going to give you, I'm going to give you like a theorem later that shows you why this is. This does not have to be true in general for the general statement of a ring homomorphism. And a good example is this. This one right here, my 2B, right? Because suppose R has an identity, then R sum R has an identity, and namely it's 1, 1. But notice the phi of the identity is not the identity here, right? I could modify this, and I could take R to the ordered pair R comma R, and then that would work. But this would not obey this. But usually when they talk about homomorphisms and rings of identity, they use this assumption. Notice this is true for this one, because the identity, the multiplicative identity polynomial rings is polynomial 1. And when you plug in 3, 7 to constant polynomial 1, you get 1. Okay. Any questions on that? Here is another definition here. You saw this word come up in the homework. The smallest natural number such that and let me remind you what this means. N times R, what does a natural number times R mean? That means I'm going to add R to itself n times. And hence my demand, that's a natural number. The smallest number n, such that n times R is 0 for all R, is if this is and in this case, we'll say that characteristic of R. If no such n exists, we say characteristic of R is 0. So, for example, the characteristic of the integers is 0. The characteristic, so for example, if you look back at this example here with the homomorphism, the characteristic of the integers is 0, the characteristic of zxy is 0, the characteristic of z mod n is n, right? Because if I add anything to itself n times, I get the identity, and that's the small, or I get the 0, and that's the smallest integer that works. So oftentimes, there are a lot of theorems actually in commutative algebra, especially the kind of stuff that Carey works on, that might depend on the characteristic of the ring. You'll see a lot of theorems that say, oh, we've solved this for characteristic 0, or we've solved this for, these characteristics. In number theory, you get a lot of results that are true in characteristic 0 and characteristic every prime except for 2, things like this.
Would you like when results are true for all times except for, say, 3? And then the problem remains extremely difficult after that?
Yeah, so I've actually seen results where, there's lots of results where it's true except in characteristic two, which is often why they say two is the oddest prime of them all. And I've seen results that are true except in characteristic 2, 3, and maybe even 2, 3, and 5. But, you know, you can probably come up with strange theorems that just have these random things where they don't work. In fact, you can probably construct things that are designed to do that. Let me give you another example. About what characteristic this ring is. Yeah, for sure. It's 2 to the n. Notice that if you add anything to itself 2 to the n times, you get the identity, or you get 0. And if you look at 0, 0, 0, and then 1, it's clear that there's an element that needs 2. What about this? We call it something else, t, correct sum. Because if you look at 1, 0, 0, you need a 2. If you look at 0, 1, 0, 0, 0, you need 4. And so there's no limit to this. And so you get characteristic 0. This example is a little bit interesting because everything in here is a finite order in the sense that everything, you pick out a single element, there is some n such that when you add it to itself, it counts as 0. However, the characteristic of the ring as a whole, because there's no upper bound, must be 0. Okay. Let R be a ring with identity of characteristic in 0. And characteristic n. So it's a ring with characteristic n. Yeah. I'm going to define a homomorphism from C to R. And this is actually a good way to define a ring homomorphism. By the way, this is just some abstract ring R, right? Any ideas how I can assign an integer n to the element of R? I mean, how can I even do that? A 1 makes all the difference in the world oftentimes. So it's clear what this means. I think if n is positive, and if n is positive, that means I just add the identity to itself n times. If n is 0, I just find it 0. And if n is negative, that means I add minus the identity to itself. Absolutely right. Everybody agrees with C. Now, I haven't formally defined the kernel yet, but the kernel is exactly what you, I think, would think it is. It's the kernel with respect to just thinking about this as a group homomorphism. So the kernel is all the stuff that goes to zero. If I want to guess what the kernel is, this is what I'm going to experience. P. N is the smallest product of integer. Such that N times 1R. And 3 if R has no non-zero zero classes. You might want to guess this last one. R has no non-zero zero classes, and it must be you didn't guess that right away. So maybe that's a sign that you have to prove this thing, huh? Okay. This. First thing, let me verify that this is a homomorphism. Okay, well, let's check this out. This is pretty clear if they're both positive, right? N plus N copies of this. And if you can go through the cases, they differ in sign. And this actually follows from earlier step that we did about properties of rings. And this is P of N plus N. Correct. And P of NM, NM again, this follows from one of our earlier propositions, but actually it's not very difficult to do this out by hand. So, okay, it's a homomorphism. Everybody cool with that? And let's check that last statement that it's the kernel, so the kernel is exact in Z. Notice that, of course, a homomorphism of rings is a homomorphism of groups. So I expect the kernel to look like this in the sense that it's got a multiple of the integers, right? Because those are what Z is a cyclic group, and so it's got a cyclic subgroup. But what does the N match? I guess is the biggest question here. So I now claim the kernel of phi, which is clear here, x and z plus the phi of x zero is precisely in. So let's verify this. Okay, let's suppose that you have something in the kernel. Better. I mean, by definition. So note. Yeah, just remember this is editor. Because this is 0, right? 0 times r is 0. So this means that x times r is 0. So what does this mean? So this means that x times anything in r is 0, right? So n is less than or equal to x, right? Now recall but notice that if n is strictly less than x, then there exists, let's say, some r and r, that r times n equals 0. Oh, and actually, almost 5. So right. So what I want to do is I want to write x. I want to divide it by n. I'm going to write it as qn plus d, where what's the let's look at it. So take this x here that's in the kernel and divide it by n to get remainder d, right? Notice that for all r and r, x times r is 0, but that's x times n plus d, right? Because I'm sorry. Qn plus d times r, which is qn times r plus d times r. Okay. And this is also 0. Therefore, d times r equals 0 for all r and r. So d equals 0 by minimality. Therefore, x is qn is infinity. So we've got Z. And let's do the other direction. The other direction is a little easier. This direction, let K in be NZ, and note R in because n times R is automatically 0. Right? So, in particular, A n times 1R, therefore, A n is in the. So that establishes the first statement. Yes.
Saying that we were not assuming that's, I was just saying it's Z's not a lane.
Oh, yeah.
It's a oh, of course. Then, but it's in the deal.
Yes, community.
Right.
Right.
That's why I was just looking
Right,
at yeah. Okay.
Okay, how about statement 2? I think we can dispose of statement 2 quickly. See how that goes. Suppose n is the smallest positive integer such that n times 1r equals 0. Notice n times 1r 0. Hence, characteristic of R. Yeah. There exists such that m times 1r 0. Then this m will work for everything, and there'll be a contradiction because yeah, there we go. R is 1 over times R. N times 1R. R 0 times R. So here's contradict minimality. So this is actually, I like this statement because this is a quick way to figure out the characteristic if you have a ring with identity. Because if you have a ring with identity, the characteristic of the ring will be the smallest positive integer n, such that n times the identity is 0. So that's a quick way to do it for ring with identity. So that's useful. How about this business about primes? R has no non-zero divisors, then n is prime. Let's do the contrapositive really quickly. Number 3. Suppose n is not prime. So there exists that is to say, n can be decomposed in a non-trivial fashion this way. Notice that 1 over R, and B becomes 1 over R, or not 0, part B. Right, because n should be the smallest positive integer since the n comes 1 over R is 0. And A and B are smaller, so these two animals can't be 0. But if you multiply, and so A 1 over R and B 1 over R are non-zero. So not prime automatically gives you non-zero. Okay, so rings without identity are sometimes much more difficult to deal with. When we get to ideals, I'm going to show you one of the many reasons why that's true, but here is kind of an interesting theorem. So suppose you have a ring without identity, then I see the tears welling up, and your little hearts are breaking, right? Mine is too. Very terrible. But there's a saving grace, because if you have a ring without identity, even though it doesn't have identity, you can kind of shove it inside a ring that does have an identity. There's actually multiple ways to do this, depending on what your original ring looks like, but here's like one of the most common. Here. Every ring in R when a ring without identity. Additionally, S can chosen to have characteristic R. Characteristic R. Or it can be chosen characteristics. So in other words, if I walk up to you on the street and give you a ring, and suppose it's like not have an identity, you can put it inside a bigger ring S with identity. Embedded means there's a one-to-one homomorphism from R into S. So you can think of R as a subring of this larger S. And if, for example, R is characteristic N, you can choose S to be characteristic N. And in any case, you can choose S to be characteristic 0. So here's how we'll do this. Let's let S but I want to take and multiply it. I don't multiply this component wise. That's not going to work for us. Here's the way we'll multiply it. This is sometimes called an idealization. So the way you add two things, R1 N plus R2 N, R1 plus R2 N plus N. That's what I mean as abelian groups. It behaves just the way you would if you stick together some abelian groups. But multiplication is a little different. Because actually, it's fairly easy to see that if multiplication with component wise, it's you're still not going to have an identity. Now, exercise. Check if this is a range, right? See what you did. It's almost like you foiled this out, right? R1, R2, R1N, MR2, and then you forgot about the MN. You just stuck it in the second coordinate. This, well, it's characteristic best is equal to 0, because actually you see, it's pretty easy to see that if you take 0, 1, you take the element 0, 1 and add it to itself any n times, you never get the identity, right? So it's characteristic 0. And the identity, yes, this is what the identity is. So what can I multiply, say, what can I multiply R1M by and get R1M back? How about this? That's my guess. Let's see what happens. If I replace R2 by 0 and M by 1, that's going to be 0. That's going to be 1 times R1, and that's going to be 0. And then I'm going to have 1 times X. So this function is if the characteristic of R is equal to N, then replace Z Z mod N to get characteristic of S. So with this construction, you can use a Z mod N instead of Z if you want characteristic that's not 0. Okay. Good questions. Okay. Okay, just enough time to tell you about a little bit about the next section. And after this first definition, this will be an ideal place to begin. Yeah, so, what is an ideal? Well, what are the most important types of subgroups of a group? The normal ones, right? The ones that are kernels of homomorphisms, the ones that you can mod out by. What are the ring? A subset in R is a subring. Again, let me say that oftentimes if you have a ring with identity, the subring is expected to have an identity, share the identity with R. A subring, but here I'm going to use the looser definition. A subring I and R, so this is just like the analog of subgroup, is called right. X and I and R and R. Rx is I. So what is an ideal? It's basically a subgroup. In fact, you don't even need subring, you just need subgroup here, but subring follows. You just need a subring that is a vacuum cleaner, right? A left ideal sucks in from the left, right? If you have R times X, X is an I, it sucks it into an element of I. A right ideal sucks it in from the right. An ideal is a left and right. We will talk more about this next time. Any questions? How many of y'all have seen ideals before? Everybody. So we'll talk more about this left and right business later and what ideals are and why we care. Any questions? All right, don't forget, I've actually got a committee meeting from like 11:15 to 12. We'll probably go to 12:30 today. But if you've got any problems, you can just roll by after that or send me an email or something. Other than that, you guys have a groovy weekend and we'll see you on Monday. Oh, yeah. Oh, I'm going to say, those for those of you out there, yes, we will have a review session tomorrow at 10 o'clock. I would meet outside here, cross our fingers, otherwise we'll roll on over the long haul. So, and those of you out there, if I can find a working room, then we'll record it. See y'all later.